Hi, everybody. It's Professor Mitchell. So this is an exciting day. We are starting our last chapter, which is chapter 8 on algebraic thinking. So in this section 8.1, we'll talk about variables. You will be able to understand and explain variables to translate word phrases into algebraic expressions, solving equations and word problems. And then finally, the formula for the nth term of arithmetic and geometric sequences. So that'll be a little review of chapter 1, I think. Variables can be used in generalizations of patterns. If we were to use actual values instead of variables, the instructions would only apply to a limited set of situations. A variable can also be an element of a set or a set itself. For example, in the definition of the intersection of two sets, A intersect B equals the set of all x, such that x is an element of A and an element of B. So in this case, x is any element that belongs to both sets. In this example, we'll write each of the following statements in algebraic form, starting with the cost of renting a car for any number of days at $40 per day. So what they want us to do here is define a variable that stands for the number of days the car is being rented. And then once you have that variable, you can say that the total cost of renting the car is $40n. So n stands for the number of days the car is being rented. Next, we have the distance a car traveled at a constant speed of 65 miles per hour for any number of hours. So if we call the number of hours h, remember that distance equals rate times time. So the rate is 65 miles per hour, and the time is the number of hours, which we're calling h. So then the distance would be rate times time, which is 65 times h miles. Next, we have one weekend, a store sold twice as many 8 gigabyte flash drives as 64 gigabyte flash drives, and 25 fewer 256 gigabyte drives than 8 gigabyte drives. If the store sold D 64 gigabyte drives, how many 256 gigabyte drives and 8 gigabyte drives did it sell? So let's pick this apart piece by piece. This is one of those problems where you read it the first time and you might freak out a little bit, but just take it, one concept at a time. So we're calling the number of 64 gigabyte drives D. So what I want to do now is look through the statement and look for something that's being compared to that number. And I see it right at the beginning. A store sold twice as many 8 gigabyte drives as 64 gigabyte drives. So since we're saying that the number of 64 gigabyte drives is D, that means the number of 8 gigabyte drives is 2D. Okay, so one down, one to go. How many 256 gigabyte drives did it sell? Well, that number is 25 fewer than the number of 8 gigabyte drives, and we just said that that number is 2D. So what we have is 25 fewer than 2D. Now be careful, fewer than means subtraction, of course, but when it says 25 fewer than 2D, be careful not to say 25 minus 2D. It's actually the other way around. Think about 2 fewer than 10. That doesn't mean 2 minus 10. It means 10 minus 2. So what we have is that the number of 8 gigabyte drives is 2D, and the number of 256 gigabyte drives is 2D minus 25. Next, French fries have about 3 calories apiece. A hamburger has about 250 calories. Mateo is on a diet of 1,200 calories per day. If he ate F French fries and 1 hamburger, how many more calories can he consume that day? So first we want to find how many calories Matteo consumed eating F French fries and 1 hamburger. Then to find how many more calories he can consume, we'll subtract that expression from 1200. So let's start with the French fries. If 1 French fry is 3 calories, then that means F of them would be 3 times F, so 3F calories. And then he ate 1 hamburger, which is 250 calories. So the number of calories in this meal is 250 plus 3F. So remember the question was how many more calories can he consume that day if he's allowed to have a total of 1200? Well, that would just be 1200 minus this total. So notice when it's written here, it's put in parentheses. That's really important. And then when you distribute that minus sign, you get 1200 minus 250 minus 3F. So the number of calories left for the day is 950 minus 3F. All right, next example. A teacher instructed a student as follows. Take any number and add 15 to it. Now multiply that sum by 4. Next, subtract 8 and divide the difference by 4. Now subtract 12 from the quotient and tell me the answer. I will tell you the original number. So I see puzzles like this sometimes posted on social media, and they really seem, like magic, right, to a lot of people. So one of the downsides, I'm sorry to say, of understanding algebra is that it makes this kind of problem maybe seem a little less magical because you understand how it works, all right? Okay, so we'll analyze the instructions to see how the teacher was able to determine the original number. So if we translate this information into algebraic form, first we'll take any real number and we'll call it n. Then we'll add 15, which brings us to n plus 15. We'll multiply that sum by 4. So notice again the parentheses, the sum is being multiplied by 4. Then we'll subtract 8, which gives you this. We'll divide the difference by 4, which gives you this. And then finally, we'll subtract 12 from the quotient. So if n is the original number, then the answer that the student is going to give to the teacher is represented by this expression. So translating what the teacher told the class to do results in the algebraic expression you see here. The teacher is told the answer obtained, and then she produces the original number. So we'll use the work backward strategy to determine what happens. Suppose the final result is R. The last step was to subtract 12, so we add 12 to reverse that operation. That gives us R plus 12. The step before that was to divide by 4. To reverse that step, we'll multiply by 4, which is going to give us 4R plus 48. The step before that was to subtract 8. So to reverse that, we add 8, 4R plus 48, and then add 8, which gives us 4R plus 56. The step before that was to multiply by 4. So we divide 4R plus 56 by 4, which gives us R plus 14. The step before that was to add 15. So we'll subtract 15 from R plus 14, which gives us R minus 1. Thus, the original number is 1 less than the result. Or another way of saying that is the result is 1 more than the original number. So if a student followed the teacher's directions and came up with the number 21, for example, then the teacher could figure out that that student's original number was 20. Okay, the next example, a little bit of review of chapter 1, I think. In an arithmetic sequence with second term 11 and fifth term 23, we're going to find the 100th term. All right, so the second term of an arithmetic sequence, whose first term is A1 and whose common difference is D, would look like this. So we know that 11 has to equal A1 plus D. And then we also know that the fifth term, remember that formula A1 plus N minus 1 times D? So they've substituted 5 for N, and that gives us A1 plus 5 minus 1 times D equals 23, because we know the fifth term is 23, which reduces down to A1 plus 4D equals 23. So we know that 11 is equal to A1 plus D, and we know that A1 plus 4D is equal to 23. So now if we rewrite A1 plus 4D as A1 plus D and then plus 3D, so we're just splitting the 4D into D plus 3D, and we know that this part here is equal to 11. That gives us 11 plus 3D equals 23. If we subtract 11 from both sides, that gives us 3D equals 12. And now if we divide both sides by 3, we get D equals 4. Okay. All right, so now to find the first term, now that we know D is 4, we can take the first equation that we made, which said 11 equals A1 plus D, and now we know that D is 4. So if 11 is equal to A1 plus 4, that must mean A1 is 7. And now we'll use our formula for the nth term of an arithmetic sequence. The 100th term would have to be A1 plus 100 minus 1 times D. And we know all of these things. We just figured them out. A1 is 7 and D is 4. And that comes out to 403. So if the second term of an arithmetic sequence is 11 and the fifth term is 23, then the 100th term would have to be 403. All right, geometric sequences. Now they want me to find the nth term of this geometric sequence, which starts off 2, 3, 9 halves, 27 fourths. So remember that in a geometric sequence, to get from one term to the next, you're always multiplying by the same number. That's called the common ratio. So, and the easiest way to find the common ratio probably is just to divide any term by the term before it. So for example, 3 divided by 2 would give you 3 halves. So the common ratio of this sequence is 3 halves. And we have this formula for the nth term of a geometric sequence, and I'm thinking it might be a good idea to actually write down that formula before we have numbers filled in. So that formula goes A sub n equals A1 times r to the power n minus 1. Okay, so we filled in 3 halves for r, and we filled in 2 for A1 because that's the first term. So now, whoops. Oh, that's our nth term. Okay, that was all they wanted. I was thinking for a second that they then wanted us to find the 100th term. That wouldn't make a lot of sense in this problem. It would be a really big number. All right. Okay, similar problem. If a geometric sequence has first term 3 and common ratio square root of 2, let's find the 10th term. So using that same formula that I just scribbled down on the previous slide, the 10th term would be 3 times the square root of 2 to the power 10 minus 1, which is 3 times the square root of 2 to the power 9. Now remember that the square root of 2 is the same thing as 2 to the power 1/2. And I'm sorry, I'm just noticing a typo here. This is supposed to be a 3. Whoops. Oops, okay. Yeah, this is supposed to be a 3. They have it right in the next step. Okay. All right, so they've rewritten the square root of 2 to the power 9 as 2 to the power 9/2, because the square root of 2 is the same thing as 2 to the 1/2. And then they multiplied the exponents. Now they're simplifying 2 to the power 9/2 by breaking it into 2 to the 8/2 and 2 to the 1/2, because those exponents can be added together. And the reason they did that is because 2 to the 8/2 is a nice number, right? It's just 2 to the 4th, which is 16. All right, so 3 times 16 is 48, and then 2 to the 1/2 is the square root of 2. So the 10th term of this geometric sequence would be 48 times the square root of 2. All right. This is a cute problem. At a local farmer's market, 3 purchases were made for the prices shown in the figure. How much does each object cost? So first we have a cantaloupe and a flower in a vase. That cost $8. Then we have a watermelon and a flower in a vase. That cost $9. And then we have a watermelon and a cantaloupe. That cost $7. So there is enough information here to figure out how much each of those items costs separately. So suppose the objects in the first 2 purchases are put together. That would come out to a total of $17 for a cantaloupe, a watermelon, and 2 flowers. We know that a watermelon and a cantaloupe cost $7. So if we were to take the cantaloupe and the watermelon away from this purchase, we would be left with $10 worth of stuff, $10 for the 2 flowers in a vase. All right. You see that? Take these 2 things away. That takes $7 off the purchase price. So that must mean that these 2 things cost $10. And that means each of the 2 vases costs $5. And now it's really easy to finish it off, right? That means that the cantaloupe costs $8 minus $5, which is $3. And the watermelon costs $9 minus $5, which is $4. And that's going to do it for section 8.1. We'll see you next time.